Howdy, just in. 7.2. Eugene, Taiwan. 25 minutes ago. There is very much going on in the region at the moment. Not only in Taiwan, we also have a huge storm hitting Japan. Yeah, that's the 7.2. And there's a whole lot of activity. 5.4, 13 minutes ago. 1 hour ago, 5.6. That's the one from yesterday, I guess. But there is very much activity. And if you zoom in, or when you zoom in, you will notice very quickly there is water rains all over Jiangsu Falls. And a little bit more to the right, like I showed already yesterday. You will find white rivers, very big one. But I wasn't supposed to make a video about this actually. That's also from yesterday. I was supposed to talk about water because I stumbled across an article on fish.org, which is some days old, 3 days, 4 days. New phases of water detected. Scientists at the University of Cambridge, England, have discovered that water in a one-molecular layer acts like neither a liquid nor a solid, and that it becomes highly conductive at high pressures. Much is known about the bulk water behaves. About how the bulk water behaves. It expands when it freezes and it has a high boiling point, but when water is compressed to the nanoscale, its properties change dramatically. By developing a new way to predict this unusual behavior. How can something which is occurring in nature, unusual? Like, isn't the whole point of science to figure out how nature works and not somehow make work nature as you wish you would like that it behaves? But anyway, by developing a new way to predict this unusual behavior with unprecedented accuracy, the researchers have detected several new phases of water in the molecular level. Water trapped between membranes or in a tiny nanoscale cavities is common. It can be found in everything from membranes in our bodies to geological formations. Yes. I wrote about this in my not yet published paper, Mountainwater, about exactly this. But this nano-confined water behaves very differently from the water we drink. Until now, the challenges I will come really after. I'll just make a read through and then I will show you two things at least. But anyway, until now, the challenges of experimentally characterizing the phase of water on the nanoscale have prevented a full understanding of its behavior. But in a paper published in the journal Nature, the Cambridge-led team describes how they have used advances in computational. I'm not a IT person. Computational approaches to predict the phase diagram in a one-molecule thick layer of water with unprecedented accuracy. They used a combination of computational approaches to enable the first principles level investigation of a single layer of water. The researchers found that water which is confined into a one-molecule thick layer goes through several phases, including the hexatic phase. Hexagon. Hexagon. The most beautiful hexagon you ever saw. Just been drawn here live for you. Yeah, there would be hexagons here. and a superionic phase. In the hexatic phase, the water acts as neither a solid nor a liquid, but something in between in the superionic phase, which occurs at high pressures, hence within the Earth, for example. The water becomes highly conductive, propelling protons quickly through ice in a way resembling the flow of electrons in a conductor. What a coincidence. Understanding the behavior of water at the nanoscale is critical to many new technologies. The success of medical treatments can be reliant on how water trapped in small cavities in our bodies will react. Yeah, just think about it. You are made somewhat 90% of water, and in every cell there is water. So it has a charge, and I have been talking about the soap bubbles and stuff. No, but anyway, the development of highly conductive electrolytes for batteries, water desalination, and the frictionless transport of fluids are all reliant on predicting how confined water will behave. For all these areas, understanding the behaving of water is the fundamental question, said Dr. Venkat Kapil from Cambridge's Yusuf Hamid Department of Chemistry, the paper's first author. Our approach allows the study of a single layer of water in a graphene-like channel with unprecedented predictive accuracy. Predictive? Yeah, I got so many things on my mind, it's a little bit hard to concentrate. The researchers found that the one molecule thick layer of water within the nanochannel showed rich and diverse phase behavior. Their approach predicts several phases, which include the hexatic phase. Yes, snowflakes, they are always hexagonal. An intermediate between a solid and a liquid. And also a superionic phase in which the water is high electrical conductivity. The hexatic phase is neither a solid nor a liquid, but an intermediate, which agrees with previous theories about two-dimensional materials. No. It's easy water. Our approach also suggests that this phase can be seen experimentally by confining water in a graphene channel. The existence of the superionic phase at easily accessible conditions is peculiar. This phase is generally found in extreme conditions like the core of Uranus or Neptune. One way to visualize this phase is that oxygen atoms form a solid lattice and protons flow like a liquid through the lattice, like it's running through maze. The researchers say this superionic phase could be important for future electrolyte and battery materials as it shows an electrical conductivity 100 to 1000 times higher than current battery materials. The result will not only help with understanding how water works at the nanoscale, but also suggests that nanoconfinement could be a new route into finding superionic behavior of materials. Some time ago I made this video conducting an electromagnetic experiment, how to overpower gravity. There's a fishing magnet and some metal sheet roofing pliers and a piece of trash here, which is aluminium, which isn't magnetic. Package stuff, aluminium foil. It's not really magnetic. Yeah, I'm not a cameraman, but there is one who knows very much about this property of water since many years. And his name is Gerald Pollak. Electrically structured water per 2013. Let's just have a quick listen to him.
pH sensitive dye. Now, these dyes are mixtures of molecules whose size is on the order of 100 or so molecular weight. And it's cool because they show you the local pH by changing color. And so this is an example of that. At the bottom is a piece of naphion, similar to what I just showed you. And all the pretty colors that you see are indicating different pHs. The main point of this slide is that the region right next to the naphion here is clear, free of dye. So it means the dyes are excluded. And as I said, the dyes are approximately 100 molecular weight. What's even more interesting than that is the color distribution. And that orange color that you see just beyond the exclusion zone means a pH of 3 or less. So a lot of protons are sitting right next to um, that exclusion zone, and fewer and fewer. And we'll come back to that because that's really important. So in terms of generality, many hydrophilic surfaces generate exclusion zones, and many solutes are excluded from it. Okay, so question 2 is this zone really physically different from bulk water? I've alluded to the possibility that it might be different, but I haven't shown you any evidence. Well, I'm not going to show you a lot of evidence because it will take a lot of time, but I'm just going to summarize most of the evidence and show you some of it. And a lot of the evidence is published, and the stuff that the rest that hasn't been published will be in my new book, which should be out in 2 or 3 months. So the first is that these easy water molecules are more constrained than bulk water molecules. They're also more stable, we found from infrared radiation coming from it. We found that the exclusion zone has a negative charge, and I'll show you those results. We'll come back to it since this is obviously central to the interests of everybody sitting here. We found also that this zone absorbs light in the ultraviolet at 270 nanometers. That number is important, and I'll come back to that one as well. We found that it's more viscous than bulk water, and we found that the molecules in that zone are actually aligned in some way. And we found that the molecular structure is somehow different from bulk water. And
So, I've been talking about mountain water. Now we have this earthquake event happening in Taiwan. There are wide rivers there, there are volcanoes there, not too far from there is a huge storm, and all these kind of things. And there has been probably some rainfalls and all these kind of things. And if you think that about geology and its connection to the weather and all these kind of things, so if the ground is wet, it's not very connected with each other. Like it's loose. If you go to a field where it's very dry, you can pick a handful of sand and just blow it in the wind. But if it would be wet, it would stick together. You could take a handful of dirt and form whatever you want to, because it sticks together. As it sticks together, it has all these properties here, and those which Gerald Pollak still talks about later in this and the other presentations he has about easy water. So water, not only that it contains whatever minerals and stuff, it is also by itself creating energy. It is energy, even though it's stuck to a surface. But it's surface conductivity, like I showed in my very sophisticated homemade video, how to overpower gravity. You just have to dip your finger into water and you can lift stuff made out of metal. It will stick to your finger even though it's not magnetic. So this means, and like with mountain water, if you have a mountain soaked with water, there's like these kind of layers, this kind of double layer in the water, which is its own, in a way, energy source. And it's working as a circuit, part of the circuitry, which therefore would make the connection to the heavens much easier since there is more conductivity in the ground just because it's being wet. Mountain water. And charge accumulates on peaks. Uh, that's a little bit. I probably should have written down something because I don't know where to continue, but I hope somehow you get the importance of water in our environment, in weather, space weather, mountain water, wide rivers, and all these kind of things. Wide rivers, many of them might be alkaline in nature because there's so much limestone. So it has its own charge. It's not neutral, which makes the whole thing very much more interesting. But anyway, all the best to the people in Taiwan. There's, I guess, quite something going on there. Also in Japan and many other places on the world. The amount of global stress is unprecedented almost. And I think it is because of two reasons. First of all, there hasn't been any time ever so much information out there just together. You can Google, YouTube, or whatever. There's like information all over the place. With your phone, you have an unimaginable amount of information available. Other stuff than just watching cat videos. So everybody would have the possibility, everybody who has this kind of possibility to use this kind of modern phone with internet and all these kind of things. Second, there hasn't been rarely so many people living on this planet ever. So this might just amplify the events, and the whole system is much more sensitive to whatever changes because there are people everywhere. Yeah, intense times. But anyway, I think I leave it here and take care. Thanks.